Are you being able to run it, or are you having any kind of problem? And then, yeah, make sure you are running it for the one that says building 3 only, like only one building. It should be there, right? Like, just to make sure. And then, yeah, and also make sure that the batch size is correct. If the batch size is really high, it will take forever to run. So just make sure you have it right. Yeah, so this batch size should be 125. I think. In the code, what we are doing first is to import. We're importing our stable baselines, and then the soft actor critic. And then we define our model. This verbose equal to 1 is saying that it's going to return some outputs. And then here we define the climate, the weather data, solar generation. Yeah.
So I changed the hyperparameters. I noticed there's 2 set of cells with hyperparameters. So I changed them here.
Mm-hmm.
Yeah, so that's correct.
Yeah.
And then I noticed that there's different ones here. So should that be consistent?
No, yeah, you just need to run it. Let me see. This is for all the buildings. You just need to run for building 3 up here.
Oh, okay.
See, so here is, okay, so yeah, let me go through the environment.
So don't run the last 2 cells?
No.
Is that what you're saying?
So, yeah.
Okay, all right, I got you. All right.
Yeah, okay, so in the example here, you need to run the one that is only for building 3 at the very beginning. Yeah, so it's for climate 1 and then this building. So here it will define the environment, and then what it is doing is that we are importing the stable baseline soft actor critic. And we define the hyperparameters here. Make sure the batch is appropriate one. Otherwise, if it's really large, it will take forever to. Okay, so make sure that the total number of time steps is this one. So in the line model learn, this is set to 7. So just set it to 15. So it runs through more episodes.
Yeah.
Just to make sure. Okay. Like if you're already running, that's fine. Just enter the maximum reward, but yeah, just set it to more episodes so it runs longer.
So you get 15 rewards, right?
Yeah, so that's the total cumulated reward for 1 year time.
And then we just, of the 15, pick the maximum?
Yeah.
The absolute max or the max?
No, like the less minimum, like the actual maximum, yeah.
Yeah, okay.
So the closer to 0.
Okay.
And then, yeah, regarding Jupyter Notebook, if you want to run a cell, you can just type Shift Enter, and it will automatically run it. You Shift Enter again, and then it will automatically run it. So here you should be getting the cumulative reward for the whole year. So first, the agent is going to start taking random actions, so the reward will be really bad. And then over time, after every episode, it will start taking updated actions. So this reward should increase or become less negative. And then if it's done running, you can just update the parameters and run it again if you want. Okay, if you want, you can leave it running, and then I can start explaining a bit more about the environment as it runs. And then we can implement some other algorithms. So yeah, we'll just go to the folder of the CityLearn environment, which you can download from the GitHub repository, as you saw before. Here is also all the documentation about it. So we have many different files. Some of them will contain information about the environment and the data itself. And then some other are some examples of reinforcement learning agents or a rule-based controller. Then the main classes that we have are CityLearn, which is calling all the building classes. And then every building will have a different class. That will be, we have the heat pumps, the electric heaters, and then we have the energy storage devices that will have different efficiencies. Then the heat pumps, there's a heat pump per every building, and it's providing the cooling energy. So the efficiency of the heat pump is given by the coefficient of performance, or COP. So for cooling, the COP, or the coefficient of performance, will be better if the outdoor temperature is colder than the indoor temperature. If the outdoor temperature is colder. The coefficient of performance is how much units of cooling energy we can obtain per unit of electricity or kilowatt. So typically we are in a range of 2 to 4 of coefficient of performance, which means that for every kilowatt of electricity we are obtaining 3 or 4 kilowatts of cooling energy. But this is influenced by the outdoor temperature. So the lower it is, the higher our efficiency, but the less cooling we need because it's colder outside. So typically, for example, for one single building profile, the environment will, if we are just trying to minimize energy consumption, then a reinforcement learning agent would try to consume more energy during the night when it's colder outside and store more cooling energy, and then release it into the building during the day when it will be warmer, and the efficiency of the heat pump will be worse. For multiple buildings, this might change because they might be trying to minimize the electricity consumption that they consume at the same time, and not only their individual energy consumptions. Then in CityLearn, we will have many different input attributes. If we go to the actual code of CityLearn, we can see all these input attributes here in the initialization function of the class. So the first few inputs into the CityLearn class are just the names of the files that it's going to read. And then some others will be like the simulation period. So if we want to simulate a whole year, we will set the simulation period from 0 to 8,759. And then the cost function, which is whatever we are trying to optimize. So the cost function, you can change it, and it's not going to have any impact on the reward. But it will just tell you how good or bad you are doing in terms of what you are trying to optimize. So there are different cost functions that we can use. You can select the ramping, 1 minus the load factor, the average daily peak load, the peak load for the whole simulation period, and the net electricity consumption. So if you select all of these, then at the end of the simulation, it will return the values of these cost functions.
So it tries to optimize those variables. That's what the cost function is doing. It's trying to get as close to...
Well, the cost function is returning these values, but then those are not the reward function. Then we have the reward function, so we need to define our reward function in a way that we can optimize our cost function. So every time you take an action into the environment, it will return a reward that you can define, that you need to define yourself.
So your term for cost function here is not the traditional use of the word cost function. Because cost function is usually, say, prediction minus observation.
It's different. No, it's not that. Yeah. I mean, that would be for supervised learning. Here is just what we are trying to optimize. It's returning these metrics so we can see how good or bad we are doing. Yeah.
So I get that the average daily peak electricity demand that you get, I mean, that's supposed to be the average, right? And the peak demand is the maximum. Mm-hmm. But when I run this, I get an average that's higher than the maximum. So how does that happen?
You get an average?
Maybe it's...
Oh, no, okay, yeah, so it's... No, so that can happen because these values are normalized. Yeah, so what we do is that we have a rule-based controller. Okay, so the thing is, with these cost functions, it will be hard to compare them with each other. Like the load factor will go from 0 to 1, and the peak function is in kilowatt. The peak value is in kilowatts, so it will be very high. So we normalize all of them by the results of the rule-based controller. So CityLearn will run internally a rule-based controller, and it will obtain these cost values for the rule-based controller, every single of them. And then it will divide every single of your cost functions by the ones of the rule-based controller.
How sensitive is this to the relative size of the variables? For instance, you've got a variable that goes from, let's say it's a standard normal variable that goes from minus, 3.6 to positive 3.6.
Yeah.
And you've got another variable that is between 0 and 1.
By variable, you mean states? Or?
Yeah.
Okay.
Yeah. That goes from 0 to 1. How sensitive is the relative size of these states to the to each other?
Well, it doesn't matter because they will be normalized from 0 to 1, all the states.
Oh, okay.
Yeah.
Yeah.
So the agent. Yeah.
So whatever method you use to normalize one, you have to normalize all of them using the same method.
Yeah. So yeah, exactly.
Okay.
So for example, that's also why we normalize them from 0 to 1 and not using the standard deviation and the mean. Because you cannot know the mean and the standard deviation in advance,
Yeah, sure.
but you can know the limits in advance.
Yeah.
So yeah, for example, let me show you. Yeah, so if I run the observation space in the environment, then I will see that there are 5 variables.
Yeah.
Box just means that it's like a continuous, they are continuous variables.
Yeah.
It's like a class. And then right in low, I can see what are the lowest values of all our states. And then high, which are the highest. So in CityLearn, we can define let me see. Okay, so this is the folder. So if we go to our building state action space, this is a JSON file that contains all the states that we want to use. So now we are using building 3, right? So here we can define what are the states that we want the environment to return when we take an action. So we are using the hour of the day, and then we are using the prediction of the outdoor temperature 12 hours ahead. So we set it to true. And then also the non-shiftable load, which is the electrical consumption of the building, regardless of the cooling or the heating loads. So we want to obtain that too. And then we also get the state of the charge of the cooling storage device. Every time we take an action on storing or releasing more energy, the environment will return this state of the charge. And then this is the action that we take, cooling storage. So this building has no domestic hot water storage, only cooling. So we have only one action that we can take. When we go to the observation space and set it to high, we can see the boundaries of each of our states. So the first state, we say it was the hour of the day, so the highest value is 24. And the lowest value will be 1. And then this 35 is in Celsius, which is the outdoor temperature, which is the other state. So we see that for that year, the maximum temperature will be 35, and we'll use it also to normalize our states. Like right now in this code, this is being done automatically by the OpenAI baseline that you are running. It's automatically taking all these boundaries and normalizing the states internally. And then, yeah, we have the rest of the boundaries for whatever the actions that we are taking, the states that we are seeing. And then we see what's the maximum and the minimum values for the action that we can take. So here, the action that we can take, the maximum value will be 1/3, 0.3, which means that we can only increase the storage by 30% or 33% on a specific hour. So every time a step, we can only increase or decrease our storage by this amount.
So that's the transition between states, between steps.
Well, this is the action that we can take. So we can take actions from minus 0.33 up to 0.33 in that range.
What units is that?
So the unit is the percentage of the ratio of the total capacity of the storage device. So if we take an action that is 33, it means we are increasing the amount of energy stored by 33% of the total capacity. Yeah. And then the environment automatically has boundaries. So if we are at full capacity, it doesn't matter that if you take a positive action, the the state of the charge is not going to increase anymore. So for example, if we want to manually take an action in the environment, again, this is internally done by the agent already. Yeah, first, let's say we reset the environment. So we reset it, so now it's returning the initial states. So the hour 1 of the first month of the year and all of that, the temperature, and then this state here is the state of the charge, which starts at empty, at 0. So now let's say that we want to take a positive action, which means we want to store some energy. Or well, let's say we don't do anything. So then the state of the charge continues to be 0 because we have taken an action that is 0. And we obtain a negative reward. So this reward is because of the energy consumption. So even if we don't take any action, there's still some electricity consumption from the building going on, from the appliances or anything.
The 2 there, is that half hour 2 or hour 2?
This 2? Yeah, this is hour 2. Yeah, 2 a.m. Yeah, this is the hour of the day. It goes to 24, and then goes back to 1. So this is, at 2 a.m. There's still some energy consumption in the building. So let's say that instead of not taking any action at all, we wanted to store something. Then we will see the difference. So now we are going to increase our storage capacity by 30%. So we can see that the reward is much more negative now. Now we are taking a lot of electricity from the grid to increase the amount of energy that we have stored in the cooling device to make ice or anything. So now the reinforcement learning agent is going to store this state, then the next state, and the reward function, and the reward that it got, and also the action that it took. So it's going to store these 4 things: the previous state, the next state, the action that it took, and the reward that it got. And this will be stored as a list, as a tuple, in order to later make all the updates. So it seems that there's a negative reward. So if the reinforcement learning agent only cares about maximizing the immediate rewards, then it would say, okay, this is bad. I took an action and then I got a very negative reward. So I will never take this action again. But it's actually trying to increase the long-term reward. So even if the current action was bad and it got a negative reward, it will continue to take these kind of actions to see if in the long run it can optimize them. Because maybe it's more efficient to store energy at 2 a.m. than to do it like at 3 p.m. Yeah, for example, let's take more actions. Let's store more, and then a bit more.
So where's the discount factor set? We didn't check that.
Yeah, so the discount factor is already 0, is the gamma. So it's already 0.99, you don't need to modify that. Let's say at this point we are at 5 a.m. and then the storage is at full capacity already.
So the way the discount factor works, the previous period has a discount factor of 0.99. The one before that has a discount factor of 0.99 to the power of 2, and et cetera, et cetera. Is that how it works?
Yeah, so in reinforcement learning, what it's trying to optimize is trying to maximize in the long run this reward plus
all previous rewards times the discount factor.
Yeah, exactly. Like the previous reward multiplied by the discount factor. Yeah, it would be like a T1, T2, and so on to the power of.
To the power of or times by?
No, to the power of. So when we are finding the Q values, with the function of the Q learning that we are optimizing iteratively all the time, what we are trying to maximize implicitly is this. So the discount factor is important depending on our problem. So we want the discount factor to be as small as we can, but not smaller than we should have. Like for example, if we are taking hourly time steps to maximize the cost savings. So let's say that we can store energy at 4 a.m. in order to use less energy at 4 p.m. because it's very expensive. So we have this 12-hour range, right? So let's say that by doing that, storing energy at 4 a.m. to save energy at 4 p.m., we can have cost savings of 20%. So then we want to make sure that our discount factor to the power of 12 is not lower than 0.8.
How does it work in the case of wanting to capture really rare events that might happen, only say once a week or even once a year? Given that the time steps here are hourly, how does the discount factor work when you're considering rare events?
I mean, the discount factor is more the time of horizon in which you want to optimize. But what do you mean by rare events?
I think the name for it in the reinforcement learning is like sparse reward.
Oh, sparse rewards.
Okay.
So
Yeah.
So I don't know much about it, but that would be the key words.
Yeah, I see. Okay, I see. Yeah, so if you have sparse rewards, which means that most of the time you are getting a reward that is 0, and then once in a while you get a positive or negative reward, then it's a bit harder to learn. But yeah, you still need to run more iterations. Maybe when you have your batch of information, you want to try to balance it a bit more, and maybe sample more from the events where you actually got a reward, and sample less from the events where you didn't get any reward. Yeah. We were discussing the other day with Spiros about balancing the data. If you have very unbalanced data, you can do that. Yeah. For this problem, it's not really the case. Like you are getting rewards constantly because you are consuming energy all the time. You want to store energy very often. Sure. Yeah, like every 24 hours or so. So we can release more energy into the building than the building can take. So if our energy stored for storage is already at 100% capacity, then even if we take a very negative action and we try to release a lot of energy into the building, if the building cannot take it, then the state of the charge will not decrease as much. So for example here, the state of the charge is set up at 100%. In this case, the storage device is sized at 3 times the maximum cooling demand for a given hour of the building. So in the summer, the energy demand of the building, the worst one might be, let's say 20 kilowatts. So then the size of the storage for cooling will be sized at 3 times the 20 kilowatt hours. So let's say that now we take a negative. So if we take a negative action of minus 0.33, then theoretically the energy storage should decrease by 0.33. So it should go to 0.66. But it might not do that because the energy consumption for cooling of the building might not be as high. So then the storage doesn't have anywhere where to release all that energy. So even if you take this very negative action, the next state of the charge might not change much, if that makes sense. Yeah, I mean, the building has a cooling demand, so you cannot release more energy into the building from the storage than the building can take. So if you want to discharge a lot of energy from the tank, like minus 0.33 or 30% of the capacity, then it might not be able to release all of that because maybe the demand for cooling of the building is not as high. So just what I mean is that the action that you take might have some boundaries in terms of the consequences that it might have in your states. So then in CityLearn, we have the class CityLearn that is calling all the energy systems that we have in the file energy models. So we have the buildings, the heat pumps, and then energy storage devices. And then they are all reading the data from this folder here. So what I did was to simulate 36 different buildings in sets of 9 for 4 different climates in Energy Plus. Let's open just one particular building. So for every building, we will have the month, the hour, and also the type of day. It goes 1 to 7, and then 8 means it's a holiday. Then if there is daylight savings status, and then the indoor temperature inside of the building. Then this is another state that we can use. it just gives information about whether we are not meeting the set points inside of the building. So it's the average unmet set point in the building. And then the indoor relative humidity, and then the electricity use of the equipment. So some of these buildings will be residential. So I took real world data and feed the simulations with it. And some other buildings, especially the office building, will not really be real world data, but it's just simulated. But I added some random noise to it. And then some of the buildings will have domestic hot water use, and then all the cooling loads that I simulated. That also include the thermal heat gains of the appliances inside of the building that have an impact on the cooling load. So there is one file of this per every building. Yeah. So for your own research on demand response, you could just simulate in Energy Plus your own buildings and create these files and then control them with reinforcement learning in any climate that you want. And then you can generate also the solar generation profile that will just have the energy generation of 1 kilowatt of one solar panel with 1 kilowatt of capacity. And then here we have all the weather data. So for the weather data, we have the real time and the predictions that we can use. Yeah, this is real world data. So here we have the dry bulb temperature, the relative humidity, and then the solar radiation, direct and diffuse. And then we have all the predictions for these same values, 6 hours ahead, 12 hours ahead, and 24 hours ahead for all these different values. So for the predictions, I just made them myself, taking the actual values, some hours ahead, and adding some random noise with different accuracies. So the longer we go into the future, the less accurate they are. The accuracies, you can find them in the GitHub repository, in the definition of the states, if you want to see how accurate the predictions are.
With the weather data, is that coming from a typical meteorological year?
Yeah.
Data file?
Typical year, yeah.
Okay. There is some issues with using TM-wide data sets too, because they represent a typical year and no year is typical.
What?
So it is a typical year?
Yeah.
One of the big issues with using those data sets is that it represents a typical year for that location, but there very rarely is a typical year.
Yeah, I see what, yeah.
It's not like real data.
Well, yeah.
It comes from real data, but it's not.
But it's not really, yeah. It's been modified, yeah. Yeah, so then we have all this data, but if we want to select it as states and actions, then we just go to the file that I showed earlier, which is the building states space. So here we can select all the different variables that we want for the different predictions and everything. So if we just want to use them in our reinforcement learning code, we just set them as true, and then when we take an action, they will be returned by the environment, as I showed earlier. So yeah, so the advantage is that it's very straightforward to do this. So then CityLearn will automatically see if any of these are true, then it will go to the data files and it will read them and output them.